Our first two speakers will be from European funded projects. I kindly ask you, Carlos, to open your video already. The first speaker will be the coordinator of the European funded Future and Emerging Technologies, so in short, FET Open project, Prime. We are very proud to be a part of this project as well. Carlos is from CSIC in Spain and will now give us real insight about this European project, which is a collaborative project on the next generation of active microfluidic devices. So with this, Carlos, please open your mic and the floor is yours.
Okay, good afternoon, everybody. Thank you very much, Andreas, for your kind introduction. On behalf of the Prime Consortium, I would like to thank the Austrian Microfluidics Initiative for giving us the chance to present our project at this event and to this community. When I was invited to this event, I was told by Andreas about this Austrian initiative. I have also investigated myself more about it. And I must say, I'm very happy to be here today to learn more about how, through this platform, you're bringing together all the capabilities and expertise of the Austrian microfluidics community to bridge the gap between basic research and real application in this area. I want to say that it's a great initiative and it's indeed an example to learn from and to follow. Well, Prime, at a much smaller scale and focus on a very specific topic, also aims to join efforts from different partners coming from different disciplines to bring novel smart materials and fabrication techniques into the scope of active microfluidic devices, as I will try to show you during the presentation today. And also very glad to be here together today with in this webinar with another very interesting European initiative, like it's the Next Gen Microfluidics platform, and I very much look forward to learn more about also this project at this meeting today. Well, I try to introduce in the next 15 minutes what is the aim and the scope of our project. And first, I try to explain to you what is the problem we aim to solve. And here you have in the left a typical image of a microfluidics lab. The current standard in microfluidics laboratories is that of a passive microfluidic device that typically requires bulky equipment to manipulate and control the fluid inside the chip. For the detection also, you need external equipment such as microscope or other sophisticated and bulky devices. And all this makes the cost of microfluidics platforms expensive, and their operation can only be performed typically by highly specialized personnel. All this obviously hinders the use of microfluidic technologies outside the research laboratory, and therefore makes difficult their penetration in application areas where the massive deployment of microfluidic chips, of microfluidic platforms is required, or where their use away from highly specialized laboratories is required. As a result, there is a need for adopting new strategies to reduce this cost and also make it accessible for non-specialized personnel. One way to do so will be to eliminate the need of all this external off-chip equipment and make at the same time the devices easier to operate by incorporating all the fluidic and all the sensing functions in the microfluidic chip itself. For fluidic functions, there have been several attempts at the laboratory level to create active microfluidic devices incorporating valves, for example, by using electroactive materials. However, they have not been translated into commercial devices, mainly due to the difficulty to integrate all these active elements by using industrially relevant and scalable fabrication methods. For the sensing side, it is crystal clear today in the days we live that the importance of having powerful sensing platforms that are easy to use and to read, ideally with very simple equipment. Okay, what we propose in Prime, what is our objective? The vision of the Prime technology, our objective is to overcome all these limitations through the use of smart materials and nanomaterials together with advanced manufacturing techniques that could allow us to integrate all the fluidic and sensing functions into a single device. This could lead to a new generation of microfluidic systems that will require a minimum volume, a minimal amount of equipment around. In Prime, we aim to develop, therefore, a printing platform of advanced smart materials able to integrate all the functional elements for the preparation of active and contactless microfluidic devices. And to do so, we are generating a platform of responsive materials that can be precisely structured, precisely positioned through 3D printing to program light-triggered deformation of these materials and implement with them the fluidic functions, that is the valves, the pumps, for the active microfluidic device. On the sensing side, we aim to combine state-of-the-art nanosensing technologies and smart thermally sensitive materials to integrate sensors in the chip channels, making them easily to read and by using an optical change of the smart material, of the responsive material that is integrated in the chip. The manufacturing technologies employed in Prime aim to make the industrial fabrication of these devices feasible, overpassing the current laboratory level attempts to generate active microfluidic devices. And we aim to eliminate all these bulky equipment around the chip that will be substituted by a chip operator system that could be ideally handheld and that will include on one side all the photonic elements such as LEDs and lasers to address the fluidic functions, to address the valves, the pumps, and on the other side, we'll also incorporate the cameras that will allow us to assess, to measure the analytical assays. Okay, and to implement this vision in Prime, we have proposed to use two scientific developments that we have in our laboratories, and one of these pillars is the technology of thermal ELISA sensing, in which by using detection antibodies coupled to nanoparticles in combination with analyte capturing antibodies coupled to a substrate, it is possible to detect the presence of the analyte as a local heating of the substrate when this is irradiated with near-infrared intense light. Okay, the other pillar of Prime, of the project, is 4D printing of liquid crystal elastomers, a technology that has been recently developed in our laboratory at CSIC, that allows this technique to structure these soft materials, liquid crystal elastomers, to create elements that can be formed in a programmed fashion, performing mechanical work as a response to an external stimulus. The Prime project counts for its implementation with a consortium formed by 6 partners, including one small medium enterprise coming from 4 different European countries, the Netherlands, Germany, Austria, and Spain. And the expertise and the interdisciplinarity of the consortium covers all the aspects needed to pursue the implementation of the proposed active devices, active microfluidic devices, going from the material synthesis, the processing, the modeling, and microfluidics towards advanced application in the biomedical field. Here there are the building blocks that include the preparation of sensing nanomaterials from CSIC, the synthesis of smart materials by Technical University of Eindhoven, and its structuring using additive manufacturing tools also by CSIC. With these fabrication tools, we are developing the sensor and the soft actuators for the fluidic functions, and this last with the input of the modeling from Max Planck Institute. The actuators will be integrated as active elements to implement the chips by University of Zaragoza that will also validate the technology together with BeyondChip. Finally, BNN is supporting all the innovation and outreach actions all over the project. Going more in detail, as mentioned before, CSIC counts with the thermolysa technology, in which we have analyte capturing antibodies coupled to a substrate. We also have detection antibodies coupled to plasmonic nanoparticles, and in the presence of the analyte, a sandwich is formed on the surface of the layer of the surface of the substrate that, on irradiation with near-infrared light, induce heating of the plasmonic nanoparticles and therefore induce detectable local heating of the substrate that we can measure. This technology provides a selective and ultra-sensitive biosensor, and in Prime we are incorporating this technology in the chip in combination with heat-mediated color read materials prepared by Technical University of Eindhoven that will allow us to optically determine the result of the test in a fast and easy fashion. TUE, Technical University of Eindhoven, is also preparing photoresponsive materials to generate the soft mechanical actuators for the fluidic functions. Light has been selected as our preferred stimulus, since it is a very adaptive trigger for actuation that can be remotely applied to the material with a high degree of spatial and temporal control over the stimuli, over the response. The excitation of these light-responsive molecules incorporated in the material introduce disorder on our liquid crystalline material, and as a result, the system contracts along the direction of preferential orientation of the liquid crystal molecules, and expands along the perpendicular direction as it is shown in the cartoon. In this way, there is no contact with the device. No contact is required with the device. We can address these actuators remotely, and we therefore can implement these mechanical functions also. We can address this mechanical function and govern the fluidic functions also remotely with light. During the lifetime of the project that started something like 2.5 years ago, we have made large progress in this respect, and we currently have a collection of materials showing this photoresponsive behavior, being all of them specifically designed to be processed using the 4D printing platform developed by CSIC. 4D printing combines the use of additive manufacturing tools, additive manufacturing techniques, and smart materials. And while 3D printing of conventional material leads to inanimate 3D objects that does with a static shape do not change their shape on time, 4D printing of responsive materials adds the time as a 4th dimension, leading to architecture, to structures that, when exposed to the right stimulus, can change their shape over the time. In the 4D printing of liquid crystal elastomers, a main chain like liquid crystalline polymer, the chains drawn in the left figure, These chains are extruded. They are digitally positioned in a substrate, and finally they are fixed by UV irradiating them, leading therefore to the final elastomer. Well, advantageously for us, during this extrusion process and during the deposition, the shear forces and the elongational flow that takes place in the process favor the alignment of the chains, of the polymeric chains along the displacement direction of the needle, and therefore this orientation allows a precise programming of the morphology of the material, and therefore a precise programming of the magnitude and directionality of the forces in the elastomer when this is excited with the right stimulus, with the adequate stimulus. As a result, the mechanical actuation of these structures can be programmed through printing, and within the development of Prime, we have extended the principles of 4D printing, initially developed in CSIC with thermally responsive materials, to the photoresponsive systems just presented in the previous slide that are being integrated with other passive materials of the chip to generate the fluidic functions of the microfluidic device. In this respect of the fluidic functions, modeling carried out by our colleagues, by our partner from Max Planck Institute, is helping very much the project in the screening and the exploration of all the design parameters and all the operational variables needed to guide and to optimize the engineering of the fluidic elements integrated in the chip, overall rising the operational capacity of our elements and avoiding forcing operational problems in the device. University of Zaragoza, with their expertise in microfluidics, is working on the preparation of chips that integrate the sensors and also the 4D printed actuators prepared by the other partners. And for the actuators, once integrated in the chip, they will be illuminated with the light of the appropriate wavelength to produce ease deformation and implementing in this way the valves proposed in the project, proposed in Prime. These active elements will be finally integrated in the specific microfluidic devices. And in particular, we seek within the project validation of the technology by generating active microfluidic devices in two relevant application cases: in vitro diagnosis and organ-on-chip applications. This part of the project is led by Beyond Chip, that will work in close collaboration with the University of Zaragoza and CSIC. Finally, as mentioned, BNN, expert in supporting commercialization, dissemination, and stakeholder interaction, and very well known to you all in this community, is supporting all the innovation and outreach action all over the duration of the project, ensuring that the knowledge that is generated during the project implementation is being disseminated to the right target groups, promoting in this way social and economical impact of all the project activities. Well, we reach to the end of my presentation, of the project presentation. I have presented what we are doing in Prime, and to finish, I would like to tell you where we would like to reach. We have recently passed half of the project lifetime, and we have done good advances in the materials and so also in the basic implementation of the sensing and the fluidic building blocks that will form the Prime active microfluidic chip. But there are, of course, still important challenges in front of us regarding materials performance and fabrication, but we are working to reach our objective. As I already mentioned, we seek to generate this industrially feasible fabrication technology that allows us to create active microfluidic chips that could be easily used by means of simple and portable devices. These devices will be used to address the fluidic elements of the chip, and will also serve to read the result of the analytical assays, trying to simplify in this way the use of the microfluidic technology, and therefore narrowing in this way the gap between the technology, the microfluidic technology, and the non-specialized end users. Despite we are focusing in validation, our validation cases in the biomedical field, the development of our technology could be extended to other application areas that could include food and water assays, environmental monitoring, or the farm sector, as well as to expand to geographical areas where economical resources are limited, or to locations where bringing heavy and bulky devices needed to run a conventional microfluidic lab are difficult to take, or expensive to take to. Well, I hope I gave you the flavor of what we are doing in at Prime, at the Prime project. I would like, of course, finish thanking the funding from the European Union Horizon 2020 Research and Innovation Program. Thanking again the organizing committee of this webinar, and of course thanking you all for your kind attention. Thank you very much.